Okay, in this video we're going to state and prove the projection theorem. All right, so the projection theorem goes as follows. Let S be a Hilbert space and let V be a closed subspace of S. Okay, so you can think of your Hilbert space S, and then you've got this closed subspace V. Okay, now if there's some x out here in S, then there is a unique V naught, okay, that is inside of V. So there exists a unique V naught inside of V that is the closest element to x. In other words, any x minus v naught is less than or equal to x minus v. So in other words, if there's another little v here inside of capital V, then v naught is closer. That's what this second statement says. And then furthermore, x minus v naught minimizes, or v naught minimizes x minus v naught. In other words, v naught is the minimizer down here. If and only if x minus v naught. So this vector here is going to be x minus v naught if that thing is orthogonal to the space V. In other words, it's orthogonal to every element in V. Okay, so the proof, we have to show, first of all, that there exists a V naught. We'll show that. And then that it's unique. And we actually, this is similar to other proofs we've seen. We're not going to show that it's unique. And then we need to show that that V naught is less than or equal to, the norm. It's the closest element in V to X. And then we need to show that it's orthogonal to V. Okay, so that is what the proof will do. I can get it change page. Okay, so we're going to go, the first step is to show that V naught exists. In other words, there's this V naught and it's inside V and it's the closest element. Okay, so it minimizes, it's not an infimum, so it's actually inside of V and it's the minimizer. Okay, so how do we go about showing that? Okay, so first of all, assume that x is not in V. Because if x is in V, remember, we've got, here's V and x is outside of here. If x is inside of V, then of course, V naught would just be equal to x. All right, so we'll assume that x is not in V, and now we're going to let delta be the infimum over all V and V to x. Okay, so we haven't yet showed that there's a V naught that achieves that infimum. Yeah, so what we need to show is that in fact there exists a V naught that's inside of V, not outside of V, but inside of V, so that we achieve the minimum. It's not just an infimum, it's a minimum. Okay, so to do that, we're going to construct a sequence. Okay, let VI be a sequence in V, and we already have established that delta is the infimum. So I mean, think of something that's kind of converging. It may not actually reach, so the distance here, would be delta, and it's getting closer and closer to delta, but maybe it doesn't actually achieve it. So we're going to construct a Cauchy sequence that VI, so that the norm gets closer and closer to that infimum. And what we want to show is, in fact, that it's a Cauchy sequence, which means that since it's a Hilbert space, the Cauchy sequence will converge to an element that is inside of V. Okay, so to show it's Cauchy, we have to remember to show it's Cauchy, we have to show that VI minus VJ goes to 0 for any, for any I and J. This is for any I and J. Okay, so we're going to use what's called the parallelogram law, this statement here, which is, again, relatively easy to show using just the property the fact that that the norm is an induced norm. In other words, the norm of x squared is going to be inner product of x with x, and then the properties of an inner product. And we can show this parallelogram law. Okay, so what we're going to do is our x up here is going to be Vj minus x, and then our y is going to be x minus Vi. Okay, so the parallelogram law, we plug those x and y's in here, and we get this term is the first term, and then we'll have a x minus y instead of a plus, and that's this term. Then we've got 2x squared and 2y squared. So this is just plugging into the parallelogram law, and then on this side, of course, you got Vj minus x plus x, so the x goes away, so we get the norm of Vi minus Vj, and this is for any I in j. And so this statement holds again, if we can show that in fact this thing is converging to Vj minus Vi goes to 0, then we know that this is a Cauchy sequence. Okay, so on the right hand side we've got this term still, and then let's just take a look at this term. This guy is going to be Vj minus a minus Vi, so that'll be Vi plus, this will be a Vj plus Vi, and then we'll have a minus x, so minus 2x. And then we could pull a 2 out here, and we'd have to divide by 2 there. And then when we take, the norm, now we could pull, or the norm squared, we would pull the 2 out, which will give us a 4 norm of Vj plus Vi over 2 minus x squared. And then we subtract it to the other side and get that term. Okay, so now let's just look a little bit more at this term here. Okay, so Vi and Vj are inside of our closed subspace V, and that means since it's a closed subspace, any linear combination inside of V. So Vj plus Vi is also inside of V. Okay, now because the infimum is equal to delta, remember we have this, the infimum for any V of x minus V is equal to delta. That means that this guy, and we had the delta without the squared, so this guy without the squared has to be at least bigger than delta. So when we square it, that term has to be bigger than delta squared. Okay, so we come back here and we know that this guy has to be, it's bigger than delta squared, and this thing has to be bigger than delta squared, and that has to be bigger than delta squared. So we know then that, in fact, Vj squared minus Vi squared, I guess we can take the first step. This thing, since it's bigger than delta, since this guy is bigger than delta squared, when we do a minus 4, it's going to be less than or equal to minus 4 delta squared. And now we know that this guy converges to 0, and that guy, this guy converges to 2 delta squared, because Vj minus x converges to delta, and norm of Vi minus x converges to delta. So this whole thing converges to 4 delta squared minus delta squared. So we know that Vi minus Vj, the in norm, converges to 0. Therefore, it's a Cauchy sequence. Okay, so we know then that Vi, converges to some V naught in V, because it's a Hilbert space. So in other words, every Cauchy sequence converges to an element inside of V. All right, so we've shown that in fact there's a V naught. So instead of an infimum back here, we could actually have plugged in here a minimum, because there is a minimizer. Okay, so we have shown here that there exists a V naught. We haven't shown that it's unique, and I'm not going to show it here, but I believe it's in the book. Okay, so we've shown that there exists a VI. In fact, it's unique. And now what we want to show is that, okay, let me just go back here to the proof. We're going to show now this next step, that in fact that V naught is the closest element inside of V. Okay, so that's step 2 here. All right, so V naught then is going to be the argmin of x minus V naught. In other words, I'm sorry, this is a V here. Oh, we want to, yeah, it's the argmin of all V here inside of V of x minus V. We want to show that if that's the case, that in fact it's perpendicular to V. Okay, that's the first thing we're going to show, is that x minus V naught is in fact perpendicular to V. So this is this statement down here that if it minimizes x minus V naught, then it's going to be orthogonal to everything inside of V. All right, so let's do it by contradiction. So suppose that in fact x minus V naught is not perpendicular to V. Okay, what does that mean? That means that there is some little v inside of our closed subspace V, so that x minus V naught inner product with that V is not 0. So let's let it be some delta. Okay, it's a different delta than before, but it's equal to some number that is not equal to 0. Now we can assume without loss of generality that the norm of this vector is equal to 1. Because if it's not equal to 1, then you could divide here by norm of V, and that would just make delta a different, smaller number, but it would still be non-zero. Okay, so let's assume that in fact this little v in here that is not perpendicular, that is not perpendicular to x minus V naught, that the norm is equal to 1. Okay, and then let's let z is going to be V naught plus delta V. So again, the idea here is this is our V naught. We're going to pick a z up here that's going to be V naught plus that delta times V, which has a magnitude of 1. All right, so what is the norm of x minus, so this is x, and this is x minus z. And we've assumed that this guy has shorter length than x minus v, and we're trying to work towards a contradiction. All right, so the norm of x minus z is going to be the norm of x minus V naught minus delta V. We've just plugged in z here. And now we've shown, remember if I have the norm of a, if I do the norm of a minus b squared, this is going to be the inner product of a minus b with a minus b. And that's going to be the inner product of a with a minus the inner product of a with b minus the inner product of b with a plus the inner product of b with b. So a with a, inner product of a with a is norm of a squared. The inner product of b with itself is the norm of b squared. And then you notice here that you have ab and minus ab. So this is going to be, we could write this as minus ab, and then, this is going to be minus ab complex conjugate. Remember, if we swap the order, then we have to complex conjugate. So if we have any complex number plus its complex conjugate, that's just the real part. So we can combine these two into 2 times the real part of, so this will be x minus this vector, or x minus v naught minus delta v. So this would be a, and this guy would be b. We're going to get the norm of a squared minus 2, the real part of a with b, and then b squared. Okay, so now what is the what's this guy? So remember the norm, if we multiply any vector by delta, this gives us, delta squared norm of v squared, and we've assumed that this guy has unit length, so that gives us delta squared. Now this guy, x minus v naught, what we can do here is we know that if we pull the delta out, we get a delta bar, but we get a delta bar, and then the inner product of x minus v naught with v, that's equal to delta. So we get delta times delta bar, which is delta, delta squared, and of course that will have a real value. So we'll have a minus 2 delta squared. So this whole thing becomes minus delta squared. And so x minus z is going to be equal to x minus v naught minus delta squared. So it turns out that x minus z squared is in fact smaller than x minus v naught, here, which is a contradiction that it's the minimizer. The v naught is in fact the minimizer. So our supposition back here that v minus v naught is not perpendicular to v is false, and therefore we've proven that if v naught is the minimizer, then x minus v naught is perpendicular to every element inside of v. All right, so that's in essence we've shown, minimizer implies this. And now we're going to show this last statement that x minus v naught is less than every x minus v. All right. Now we're going to suppose that x minus v naught is perpendicular to v for every little v in capital V. And x minus v naught is perpendicular to v. Okay, so suppose that this is true, period. Then for every little v in capital V, so in other words, we have v, we have x, we've got v naught, and it's perpendicular. So now let's pick another v outside here that is not equal to v naught, okay? And let's look at this norm. And what we want to do is show that the norm here of x minus v is in fact bigger than the norm here of x minus v naught. This is x minus v naught. All right, so what is x minus v? So the norm of x minus v, this is a very standard trick. What we're going to do is we're going to add and subtract v naught in here. So since we can add and subtract v naught, this is still x minus v, and so we have equality. All right, so now let's break this guy up according to our previous rule. That's going to be the norm of this guy plus 2 times the real part of the inner product of this vector with that vector. So that's that guy. And then we'll have the norm of this last vector. All right, now what do we know about this vector, the inner product of x minus v? Well, we know that x minus v is orthogonal to everything inside a capital V, and v naught is inside capital V, and v is inside capital V, so v naught minus v, this has to be inside of capital V. So this inner product is 0. All right, so we get that that's equal to this guy. And of course, v naught is not equal to v, which implies that the norm of v naught minus v squared is not equal to 0. So this is in fact greater than x minus v naught. All right, so we've shown in fact that x minus v naught is the smallest. And any other v that's not equal to v naught makes this a strict greater than or equal to 0. So if we come back to the theorem, we've shown, in fact, that v naught is the closest element to x. In other words, x minus v naught is less than or equal to x minus v for every v in v naught. Okay, so we have proved the projection theorem. And let me just say a thing about how important this is. Again, what we're saying is that if we have a Hilbert space and we have some subspace V, typically what we want to do is we'll have some x inside of S, and we're trying to approximate x in a particular subspace. And so we want to find this approximator, V naught, inside of V that is somehow closest to it. And what the projection theorem says is that the closest element is, in fact, that there is a closest element, and not only is there a closest element, but that it has this property that it's, in fact, orthogonal to everything inside of V.